Good day, and welcome to CFE Media's Visual Training Week. For this session, Edge, Fog, Cloud, Issues and Overview, we'll be joined by Ed Kuzemchek, CTO of Software Design Solutions, and Arlen Nipper, co-developer of the MQTT messaging protocol and president of CirrusLink. I'm Kevin Parker, an editor with CFE Media and Technology. Following our presentation, be sure and stay tuned for a live Q&A on Zoom that will begin at 12:45 Central Time. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentations. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. This virtual class session is designed for technicians, engineers, and managers who want to better understand how the merging of information technologies and operations technologies is leading to industrial environments characterized by compute power highly distributed and based on computing power highly distributed based on the nature of the data and its applications. Focusing on the challenges and issues, technologies, infrastructure, and applications will be assessed. You see before you the learning objectives for this session. Here are some tips to help you get the most from today's webcast. Attendees are eligible for 1 PDH credit for this event airing on October 9th, and is categorized within the technical, health, and safety, including core technical category for RECEP. This event is a live educational session presented on October 9th, 2020, and on demand afterward. I'd now like to introduce today's speakers. Arlen Nipper brings more than 40 years of experience in the SCADA industry to CirrusLink as president and CTO. Arlen was one of the early architects of pervasive computing and the Internet of Things, and co-invented MQTT, a published subscribe network protocol that has become the dominant messaging standard in IoT. Arlen holds a bachelor's degree in electrical and electronics engineering from Oklahoma State University. Our first speaker will be Ed Kuzemchek of Software Design Solutions. Ed is the Chief Technology Officer and Director of IoT and Embedded Systems Engineering at Software Design Solutions, an Applied Visions company. He founded Software Design Solutions in 2003, focusing the company on embedded systems, machine-to-machine, and IoT software development. He led the growth of the company from inception to its acquisition by Applied Visions in 2016. Prior to founding Software Design Solutions, Ed was Chief Software Architect for Digital Signal Processing Tools Group at Texas Instruments and a member of Tartan Laboratories, which developed highly optimized compiler technology for embedded systems. Ed holds a Master's of Science in Computer Science from the University of Pittsburgh. He is the author of several patents on embedded system software. Thanks, Ed, for joining us today. The floor is yours.
So thank you, Kevin, for having me on. Today, we're going to be talking about fog and edge processing in IoT, and specifically how you can be more successful in your IoT deployments by understanding the unique capabilities and roles of each of these in your complete IoT system. So let's begin by looking at the classical three-tier architecture of an IoT system. Many of you are familiar with this, but I just want to make sure that we're all using the same terminology for the same things, because sometimes things can have different names, and there's a constant conversation, I would almost call it a battle, about what constitutes edge and what constitutes fog, and so we'll talk about that a little further on in. And the real answer is it doesn't matter. But generally, IoT systems are defined to have these three layers. There's a cloud layer that is where all the data ends up eventually, and that's what most people think of when they think about IoT. We're going to leave that aside for now, but just just understand that that's where all of your big data analytics and all of your dashboards and all of the things that you see on primetime commercials from the big cloud vendors are telling you that IoT makes IoT great. We focus on the two layers below that. One where the very bottom here is at the edge, and true to its name, this is where the actual sensors are out at the edge of the system touching the physical world. And that's what I tend to use as the definition of an edge device, is some kind of computing hardware that is sensing a physical phenomenon. That might be temperature or vibration or humidity or light, activations, of a machine, anything that can be measured. The device that measures it, we tend to call an edge device. So those sensors report their data often to a middle layer, what we often call gateway computers. And those computers are going to do some amount of very little bit of processing to possibly quite a bit of processing. And that's going to be a discussion in this session. But that middle layer, the processing that goes on there, we tend to call it fog. And that's a cutesy little title that was brought up because it's the cloud brought down closer to the earth. And that's really what fog is. So as we think about these layers and we consider costs of equipment and return on investment, it's really important to consider the number of devices that occur at each layer. Up at the cloud, I tend to think of the cloud as one thing, even though it might be thousands of computers, but it's still one big scalable thing. You need more compute power, you write a bigger check, you get more compute power. Need more storage, write a bigger check, get more storage. And so we kind of consider it to be one thing. But here at the fog, that's usually systems that are on-premise. If you have a manufacturing facility, and let's say you're stamping out metal parts in this facility, and you might have 6 lines running, and there's a whole bunch of stages at each line, and there's a lot of bearings and turning things and things that can break. And so you may have one gateway computer actually collecting all the data from all 6 lines. You might have one on each line, but you're going to have basically on the order of tens of kinds of devices in your IoT deployment. But out at the edge, you may have thousands, hundreds of thousands, or even more edge devices. And so the reason why this is important is when you're considering costs and you're considering return on investments, a few dollars saved on an edge device can mean a whole lot of dollars saved on deployment, and it can really impact your return on investment. A few dollars saved on a gateway device, not nearly so much. So you can put a few more dollars into a fog processing system because you're not building as many of them, especially if it means you can make your edge devices dumber. So let's look at a larger picture of this 3-layer system and kind of flesh it all out. There's a whole lot going on here, so I'll spend a little bit of time on this slide. So same kind of thing. You have the edge, the fog, and the cloud. The edge sensors are sensing physical things and sending that data to the fog, and then that data eventually gets sent up to the cloud. But there's more going on here, and a lot more that can go on because the fog has the ability to do a great deal of processing at its layer, and that includes machine learning. And of course, you're going to hear folks say, "Oh, we do machine learning out at the edge." That's possible. We're going to make the claim here that the machine learning that we're interested in doing is machine learning that utilizes multiple values from multiple sensors You can do simplistic machine learning out at a sensor and do some things where you're doing fancy filtering or doing pattern recognition for a particular sensor. But to do interesting levels of machine learning at the fog level, it's important to have potentially more context. And that's the important thing that we think about. So when we think about context, we think about the edge device. Maybe it's a temperature device, or maybe it's a vibration sensor. It only knows one thing. It knows I'm measuring the vibration on bearing number 12 of stamping machine number 6 on line 2. And that's all I do. And you're going to get a lot of data there, and potentially more than you ever want to send up to the cloud, by the way, because let's say that that thing collects, maybe it collects a kilobyte a second, because it's vibration after all. Well, that's a kilobyte a second, but there's 86,000 seconds in a day. And so now you're sending, so now you've got, 86, what is that, 86 megabyte, 86 gigabyte of data per day. You don't want to send that all up to the cloud. Think of your cellular bill if you're sending it cellular. So now the important thing is to do some of that processing at this middle layer. That fog-based computer can have a good deal of the same machine learning that you would have up at the cloud layer. And it can be doing processing and saying, that's good vibration, that's a bad vibration, and sending the answer. So that's why here we have things like pattern matching, filtering, image processing. Those are good examples of fog-based processing. Now, what doesn't happen well at the fog or the edge? Things that require a very global scope, things that require looking across many, many different sensors. When you want to compare the temperature of this system with the temperature of its neighbor, or the temperature of a bearing in your site in Idaho versus the temperature of a bearing at your site in Miami. And you want to start comparing those things and doing things like preventative maintenance, asset health, those kind of things. That takes global scope. And that's where the cloud really comes in. So let's break each of these down and talk about, I mentioned at the outset of this, that we talk about where's the right place to do the right kind of processing. And it really comes down to, the answer is sometimes it depends. It depends on what can you afford to do processing. In other words, if your edge device can plug in the wall and has Ethernet access, I'll start to claim it's not an edge device, but let's say that you say that it can, then you can do a whole lot of processing and a whole lot of bandwidth. But many of the edge devices that we deal with are running on a battery. They might be wireless, or they might be low-end wired. And so you've got to have very power efficient systems. You are wanting to run very low latency, real-time kind of processing, as I mentioned, doing things like vibration sensing. And at the same time, if you remember our triangle, the edge devices are at the bottom of that triangle. You've got your tens of thousands of devices there. And so you're very cost sensitive. If you can, get rid of, say, an Ethernet MAC or a Wi-Fi radio in the edge device and replace it with a simple, maybe SPI wired or RS-485 wired interface, now you can save potentially $5, $6 on that edge device. And you can start to, add that up quite a bit. Now you may have many, many environments where you have to be wired because, one of the things about edge processing is in an industrial situation, you often want to add sensors to an existing piece of equipment. You're not really interested in going into your manufacturing facility and saying, well, let's just throw away all this equipment and get all new IoT enabled equipment. The folks who run capital expenses are not going to be very happy about that. But if you can come in and say, look, let's do an upgrade. Let's do an add-on of sensors to this equipment, and it'll run another 10 years. So that's where edge processing really comes in handy. But the situation it has to live in are all the things that are on this slide. Very little communication bandwidth, very harsh environments, often battery operated. The flip side of that is fog processing. I generally think of fog processing as gateways that are plugged into AC power and have communication going downward that is low bandwidth, but at least also low latency. And what I mean by that is, you might be kind of talking to a sensor, but we might be talking wired to that sensor, or a wireless protocol that doesn't have any real latency like IP does. And then upward toward the cloud, we have a very high bandwidth connection, Ethernet, Wi-Fi, something like that. That might not always be the case. It might be satellite, so you might not have a lot of bandwidth there. So there's a lot of different things to consider. But at the very minimum, you often have, because of your triangle that we mentioned, fewer gateway devices, so you can spend a little more money on them. Maybe that can be a high-powered multiprocessor, microcontroller. And what you can start to do in these fog processing units is image processing, localized machine learning. What I mean by that is, this is machine learning that is not taking into context large sets of data across different machines, and it's also pre-taught. In other words, you've run your learning remotely and now downloaded onto this. But I think that this is an opportunity to take advantage of the fact that you have both near access to the data. And what I mean by that is, you have very low latency access to the data. You have very, very low opportunity for failure of not receiving data. And then you have a lot of horsepower because you can plug it in the wall, and that's important. So I talked about a three-tier architecture of edge and fog and cloud, and everything kind of makes sense because there's so many other three-tier architectures in engineering and computer science that it all makes sense to everyone. And now I'm going to kind of toss a curveball here, that we have a potential paradigm shift coming by these low-cost cellular data modems and plans, where the edge devices could communicate directly to the cloud. You see this as the technologies here are narrowband IoT and LTE Cat-M1. These are technologies where people have been doing remote sensing and sending cellular data since cell phones were built, but at the same time the costs were very high. The cost of the modem was high. The cost of the plan was high. So now we're having this paradigm shift where we have the opportunity to have very low cost devices. They may be in the low teens in terms of dollars. Very low cost plans, single-digit dollars per month, very low single-digit dollars per month, and this is very useful in what we tend to call remote sensing situations. So somewhere that you don't have good access to Ethernet, but at least you have a good cell phone plan. This is good in the middle of in the middle of the contiguous 48 states. It may not be good in every situation. You might have to switch to something like satellite. But I think this has a lot of very promising future uses. It won't take out every instance of gateways that are out there, because you still have a lot of challenges in terms of cost. As we mentioned, edge devices, cost is everything, and also battery life. Wireless communication, cellular communication is not cheap on batteries. And so you're always going to have this trade-off where it may be worth it to do in this instance because of what you gain. So let's talk about return on investment. How do you start a project and start working toward computing your return on investment? The most important thing that we recommend is do something quick. And what we mean by that is, don't get into analysis paralysis. Don't get into this design heaven of trying to cost reduce your system down to nothing right away, trying to figure out how to build 50,000 of something. We highly recommend going off and getting some off-the-shelf sensors, off-the-shelf gateways, pre-built communication protocols like MQTT, which you'll hear next, and very simple analytics. Doing this will allow you to collect some data and do some very simple analyses on it. Partner up with someone who's done this before, but still, do that very quick proof of concept project and see what you get. Often, time and time again, people get surprised by the data that they get and realize that, oh, we need to shift a little bit. We need to take a little 15-degree turn and collect slightly different data because of what we actually saw during this proof of concept. So to summarize here, IoT systems need a proper architecture effort. There is these 3 tiers, and understanding how those tiers interact and what processing can be done at each tier is key to having a successful deployment. Prototype early to determine these return on investment points. Figure out what data is worth collecting, because what you initially thought is not always 100% the set that you ought to be collecting. Don't give up on fog processing. It has many benefits that can be shown. And of course, keep an eye on the future. Look out for these low-cost cellular data plans. They're going to disrupt the landscape a little. Won't take out every gateway and make it obsolete, but there's going to be a lot of situations where this tends to make sense. And so I'm going to now turn this over to Arlen, who will talk a little bit more about MQTT specifically.
Thanks, Ed. That was great. I really appreciate the outline that you did on the edge, fog, and cloud. So I'm going to switch gears a little bit, but I'm going to stay on edge, fog, and cloud, because we've got to talk between edge, fog, and cloud. And one way to do that is using MQTT. So the title to my presentation, Using MQTT and Sparkplug to Decouple and Provide Machine Models. So this is 2020, and the reason I say that, as Kevin said in the introduction, I came out of Oklahoma State in 1978 and got to work for Coke Oil. And we were using poll response protocols. And so we've been using poll response protocols for the last 40 years. And in a lot of operational systems, whether it's you're talking about SCADA or remote asset monitoring, we still kind of got this mentality, if you will, of, well, to get data, we must ask for it. But if we're really looking at designing architectures that will scale into the future, the first thing that we need to look at is what technology can we adopt where we decouple. We don't connect devices to applications. We connect devices to infrastructure. And then we can plug applications into that infrastructure, or we can unplug them out of that infrastructure. So that gives us the one-to-many architectures that we need. Number 2, which is huge, especially as we start providing data to more and more consumers off of the edge devices, off of the results of our fog computing, even back down after observations from maybe machine learning in the cloud, is a single source of truth for our models, our assets, and our tags. In other words, what we've seen a lot of is that people will engineer a system where they say, oh, Arlen, we've got to get all of this operational data, we got to get it into the cloud. Well, what happens is they end up with terabytes worth of measurements, if you will, in a data lake. And now they've got to invest yet again for the IT staff or the consultants to be able to take the tags, the pressures and temperatures out of those and give them context. Where did they come from? What were their engineering units? What was the timestamp? How do you associate all that information? And then finally, in a lot of the applications that we do, we've got to show that we still know what a superior operational solution is, because some of these systems, edge, fog, and cloud, go into systems that are actually monitoring and controlling equipment. So we can't just bypass the fact that we still have to understand how operational technology, SCADA, PLCs, RTUs, flow computers, All of that stuff works together. So the MQTT has been shown is that it's really become one of the dominant transports, if you will, in IoT. The interesting thing to me as one of the co-inventors is that it was developed in 1998, 1999 timeframe on a project with Phillips 66 pipeline in Bartlesville, Oklahoma. So it actually was invented for a real-time midstream pipeline control system. And what had happened is that Phillips 66 got one of the first TCP/IP-based VSAT systems from AT&T. And they realized that polling over VSAT system is slow. And in 1990s, it was very expensive. You literally were paying by the byte. So it's interesting to watch this migration as it's been adopted by all of the major cloud platform providers, Google, Amazon, Microsoft, IBM. But now we're seeing it transition back down to where it was originally invented for. Now, these two slides or two trends are the 2018 survey that the Eclipse Software Foundation has done, where they went out and talked to IoT and IIoT solution developers and asked them, what transports and what technology were they using. So again, in the last 20 years since MQTT was first put out there as an open standard, all the major cloud service providers are supporting it now, mainly for the ingest of IoT and IIoT type of information. Several of the leading SCADA HMI providers also provide it out of the box, as well as numerous sensor and controller OEM device manufacturers. So we're seeing it become more and more prevalent as time goes on. Now, first thing we'll do, a real quick overview of MQTT. Simple and open. When Andy, Stanford Clark, and I started on this, the microprocessors, as Ed said, this was edge, or fog, if you will, in that terms. We had 8-bit microprocessors and maybe 64K of RAM to work with. So kind of the constraining factor there is, at that time, it had to be very simple and open. Extremely bandwidth efficient. Again, we were paying by the byte. So everything that we did, we looked at, billing and things like that in that time frame. And Andy and I figured out that every byte that we could save for some of our large customers, every byte that we could save for the messaging could result in $1 million a year saving for a customer. So Andy would come in and say, hey, Arlen, I was in the shower and I just figured out how we could save another $100,000. So extremely bandwidth efficient. Now, the third point here is stateful, and that's required at the OT level. In other words, we can utilize TCP/IP, make these TCP/IP session connections, and we can utilize all of the benefits of being able to publish data, report by exception. But if we don't have state, we can't do command and control. So if I'm monitoring a valve out in the field or a pump out in the field and I lose my network connectivity, we need to have some way to inform the applications that are subscribing to that information that that device has just fallen off the TCP/IP network, and then be able to take appropriate action. In many cases, that means we need to stale the information on an operator dashboard, or if we're going into cloud, into a time series database, we need to mark the time that all of those measurements in the cloud went stale. Fourth thing it does is provides us decoupling. In other words, we can design devices, edge devices, fog devices, that can publish information, not caring who subscribes to it. So we're decoupling in that I can have an edge device that's publishing a pressure, and I don't care if one application is subscribed to that pressure or 100 applications are subscribed to that. And then, as you can imagine, late 1990s, one of our biggest challenges was Andy and I convincing IBM that the standard needed to be open. In other words, I had just come off of 25 years in that industry of having to deal with proprietary protocols. You couldn't get the specifications, you couldn't get the information on how they worked. And then the last point, of course, in today's environment is it's got to be secure. Now, Andy and I kind of cheated on that in that we built MQTT to set directly on top of TCP/IP. So what that means in 2020 is that we get to leverage the latest TCP/IP standards for our security. So right now that's TLS security. Next week, next year, 10 years from now, that is going to evolve, and MQTT will be able to stay up with that. Now, the other thing I would just want to point out very quickly is that MQTT is a remote originated connection. In other words, the edge devices in the field, the fog devices in the field, make an inbound TCP/IP connection into an MQTT infrastructure. Now, from a security standpoint, what that means is you don't have to have any ports open out in the field. So think about typical architectures where I've got a central computer. It's got to know, as Ed was saying, it's got to know the IP address of those hundreds or thousands or tens of thousands of devices. Those devices have to have ports open out in the field so that I can connect to them. By utilizing MQTT, I don't need to know the IP address of any of the remote devices. All I have to do is secure the socket that I have open on my MQTT infrastructure. So it's an order of magnitude simpler and an order of magnitude more secure. Now, we've talked a little bit about MQTT. Where was it originally designed? What was the use case? So now let's fast forward. So again, the beautiful thing about MQTT is that you can publish anything that you want on any topic. Speaking at universities, speak to electrical engineering group or a computer science group and say, how many of you students out there know OPCUA or Modbus or Allen Bradley DF1? And nobody raises their hand. But if I ask that same audience, how many of you have a Raspberry Pi with Node-RED and you're publishing messages to Amazon or to IBM or to Google? And almost everybody raises their hand. Now, again, it's very simple. You can come up with any topic that you want. You can publish JPEG pictures. You can publish XML documents, JSON documents. But that's the bad thing when we start getting into trying to be interoperable. So what the Sparkplug specification sets out to do is it defines an OT-centric topic namespace that we can all agree on. Now, what's the benefits of that? Well, if I know my topic, I can go into an architecture as an MQTT client, and I can do a wildcard subscription, and I can plug and play auto discovery. In other words, in Sparkplug, the group, node, and device tells me, where did this data come from? The birth topic tells me, oh, it came from this location, and I have a new device to discover. The data topic tells me that I've connected, I've found this new device, and now it's publishing information, updates to me, report by exception. The command topic lets me do bidirectional communications for command and control. So I can publish a valve open command on a topic and be able to actually have bidirectional command and control capabilities. And then lastly, remember we had the birth that established that, hey, we're here, but we've got to have an associated death that says, oh, we're not here anymore. So that's the first thing. Get a topic namespace that we can all agree on so that we can be interoperable. The second thing the spec does is it gives us the ability to define models and asset structures from the edge. So the Sparkplug template definition allows a birth message to define a data model. Then the template instance of the birth allows me to create associated assets from these. And then those assets will have our measurements, our process variables. Now, think about it. This is important because we're all dealing with machine learning, and we work a lot with Amazon. And part of that is, the machine learning service that they have is called SageMaker. Well, SageMaker requires a model, and I'll go back to my original point. If we're just throwing tags up into the data lake, and then we want to do something interesting with that, we've got to hire people to be able to take those tags out of the data lake and craft them into a model so that we can do our machine learning, which is probably very ironic because we probably already had that model defined all the way down to the edge device. As Ed said, is that we probably already know what that looks like. So why don't we just add that to our birth message and be able to build the model all the way from the edge? Now, again, the original intent of MQTT was to be lean and mean. We had to be able to work over those last mile connections, that cellular, VSAT, radio. So Sparkplug defines a very efficient binary encoding of process variable objects, right? Not a register value pair, but an object that represents a measurement. That object has a name, value, timestamp, data type, engineering units, ranges, quality, and any other custom property that you want to build into the process variables that you're defining. And then lastly, it defines that state management. And with proper state management, that means we can do report by exception. That means we can do bidirectional control. And it means that we have the capability of store and forward. If you think about a poll response system, if the network goes down, you're going to have holes in your time series database. But with MQTT, the client at the edge knows when the network went down. It can take those process variable objects, put those into a queue, so that when we reestablish our MQTT session, we can publish that historical data and we do a gap fill so that we don't have any gaps in that time series database that we're looking at. So ultimately, Sparkplug gives us the ability, it's an open specification, that establishes a single source of truth for models, assets, and tags or measurements at the origin. And then everybody else upstream knows that they're working with the right data. One of the notions that I've got is that, when we're in that Gartner, that Gartner hype cycle is that, hey, 6 years ago, the industrial Internet of Things was going to take off. And here we are now, 6 years down the road, and we're still kind of, there'll be a little bit of movement here, one successful project there, 5 projects that didn't quite make it because they became too expensive or they didn't result in the ROI that the customer wanted. But my notion is that we need to be able to scale our fog edge cloud capabilities. We need to scale like the Internet of People did. The Internet of People scaled because there were 2 open technologies available. We had HTTP, which defined a way to send data over the internet. And then we had HTML that said, okay, given HTTP, I'm going to define what's in those messages. And we resulted in HTML. And literally, the Internet of People exploded on those 2 base technologies. Well, we need to have that same notion for the industrial Internet of Things. And we have both pieces now. We've got an open transport protocol that is very well known across the board as far as from IT all the way down to OT. And now we have Sparkplug that defines what can be in those MQTT messages. So if you want to learn a bit more, as I mentioned, Sparkplug is open now. CirrusLink have contributed the entire specification and all the reference implementation code to the Eclipse Software Foundation. So the Eclipse Tahoe project is where all of that lives. That's where the Sparkplug spec and the reference implementation in Java-C, JavaScript, and Python live. And then there's also the Eclipse Sparkplug Working Group. And this is a group that has been formed that will allow us to finalize the Sparkplug specification, get it out there, and get industry to start adopting it. So both of those are a very good resource if you want to learn more about Sparkplug, as well as Eclipse has the PAHO project, which is probably where 95% of all MQTT implementations start as well. So in summary, Fog, Edge, Cloud solutions need proper model asset tag definitions in order to replicate at scale. Again, having that ability to just plug something in and it works. Number two, Fog, Edge, Cloud solutions need to be efficient. If we can't get that all the way down to that last mile, that cellular, VSAT, radio, then we've not accomplished what we needed to do for IoT. And then, of course, these solutions must be able to leverage the latest TCP/IP security models. So with that, Kevin, I'm going to hand it back to you.
Well, I appreciate it, Arlen, and I want to thank both you and Ed for what were some really great presentations. For our listeners, we look forward to seeing you in the live Q&A session immediately following. Be sure and have your questions ready. Thanks for joining us, and we hope the information provided will suit your purposes. Questions will be answered in a live Q&A on October 9th, 2020 at 12:45 p.m. Central, 1:45 p.m. Eastern. Participate in the live Q&A with your Zoom invite details. These details can also be found in the Additional Resources tab on the left-hand side of the screen.